Alrighty, so let me just double check to make sure that the live stream is on. Yep, it is on. It just has a little bit of lag time, and I can see a lot of you. Well, I shouldn't say a lot. 12 of you are already here, so that's good. All right, excellent. And we got about 3 minutes and a half before the class starts. So if you have any questions, you can go ahead and ask those questions in the text channel. And today I'm turning on the webcam because I think yesterday or on Tuesday, because I have left OBS on for a long time. So I guess somewhere along the line there was a lot of lag introduced, and it just got accumulated over time. So hopefully today is not going to be quite as bad as the other day. Well, otherwise I can always just turn off the webcam too. It's not a big deal. And I'm just going through the members of this server, making sure that I'm not missing anyone. So everybody who has their nickname changed, are now students or have the student role. Alright, so there's a question for today's lab. We have a couple of days to submit it. The answer is no. The other lab, I let you guys turn it in a little bit, with a little bit more time. Just because it's the first time you're using LogicSim and a lot of stuff is new. Well, guess what? Today is not so new anymore. So I'm hoping that most people have a chance to kind of review the concepts they have learned, because we're going to reuse those concepts today. And if people have not reviewed those concepts, and those concepts appear to be just like new today, I think those people will be spending a little bit more time. It's going to be pretty close to 9:50 before they're done. Yep. Good evening. Hello. And we got another minute and a half before the class starts. And I noticed, I actually looked up the schedule, the Lowe's Real schedule, and I realized that I am the only person who teach computer information science classes in synchronous mode. Everybody else are doing either hybrid or just asynchronous. That was a little surprising to me, because I thought more people would be doing synchronous mode online classes, but that was not the case. So that was just surprising. It's neither good nor bad, just I didn't expect it. Oh, there was another one at FLC? Okay. Alright. We got about 40 seconds to go. And let me see, what is that little icon there? Panda wave. Okay. Yeah, Kung Fu Panda, by the way, is one of my favorite movies. The first one is the best. The other ones they're good, but the best one, the first one is the best. Yeah, that's what I think too. Bernard, I agree with you, because I think being able to interact is important. It really shortens the turnaround time, because I can look at a question in the text channel. You guys can even send me screenshots, and then I can respond right away. So I think that is actually helpful. Yep. Alrighty. Okay. Alright, so it is time to get started. So this time I'm not using Joplin to type this note here. This time I'm just using VI. Let me kind of pull VI in so you can take a look. I don't know about that. I mean, synchronous mode is like super duper easy, right? I mean, you just get OBS, you get YouTube, and Discord. I mean, for this class, I can't really do Discord go live, just because it's a huge class. But for all my other classes, go live, has enough capacity to do it, and it's like super duper easy. Oh, well, I'm talking about mostly computer information science, professors, right? I mean, I'm not talking about humanity professors. Anyway, today I'm not using Joplin. Today I'm just using VI. And let me just emphasize one thing, okay? I'm not trying to get you guys to use VI in this class, so do not feel that you're pressured or you're required to use VI. VI does have a learning curve to it. So when you're combining that learning curve with the actual stuff and the actual content that you're supposed to learn from this class, all the concepts, it can be a little bit too much. Okay, so please, do not think that you have to use VI. Use whatever text editor you want to use later on when we are starting to actually write code. Okay, so just want to make that very clear, because last semester, one student thought that VI was required, and spent a lot of time to try to learn VI, and I mean, that's a personal choice. What is VI? VI is the editor that I'm using here. It's a very it's an editor from the 80s. I mean, that's probably one way to put it. It's very commonly found in Unix slash Linux type of environment, because you can use it over SSH or any type of telnet, very slow connections. If you have a 1200 BPS modem, not a problem. Okay, that's the kind of editor that it is. Yeah, Vim. Okay, so VI is the original name. Vim is VI improved, and then NVim is NeoVim, which is basically just new Vim. So it's new VI improved, and that's what I'm using here. It has a lot of extensions. So right now, the extension that I have is called Markdown Previewer. So I can actually type on one side, and it will refresh on the other side, as a part of the web browser. In other words, it fires up a little web server on its own, and that server is interacting with the web client, which is the browser, and it's pretty good. I mean, it keeps itself up to date most of the time. All right. Yeah. So when you become, I guess, when you become a professional, and you really have to type a lot, and and you need a very efficient way to do your editing, VI is extremely, efficient. Even though it's difficult to learn, it is actually very efficient. The whole point of VI is your fingers, stay on the home keys. So your left finger, I cannot remember your second finger on your left hand side, it stays on the F key, and then the other one stays on the J key. So you never have to move your hand to the cursor keys and page up, page down, and stuff like that, because everything can be done using the quote-unquote regular keys. And that, to some people, and I agree, it does mean efficiency. So but it's a very kind of subjective thing. So I'm not going to get too much into it. If you want to get into it, you can find tons of tutorial of how to use VI, but it does take time to get used to it. So just be warned if you want to kind of get into it. Alright, so enough about VI. I'm going to disclose the solution of the circuitry on Discord, so this way you guys have a copy of that. And let's see, I cannot remember where I put it. That's a pretty typical thing that I do, kind of forgetting where I put my stuff. And that's not it. Huh. Alright, so let me try the other place. You cannot see it because oh, there we go, found it. And there we go. All right. So this is the file. If you are not 100% sure that yours is working, you can use mine, for the lab today, because the lab today requires the use of the lab from Tuesday. or some people are turning it in today. So that's for you to download if you want to. That's up to you. All right, so that part is done, and these are check boxes that I actually cannot check, because if I want to check it, I have to check it inside VI, inside the file content, like this. So now it's checked. And then the second item is some of you might have noticed that under text channels on the server, I have a text channel called Study Habits. Anyone can contribute to that channel if you have any type of tips, any type of study skills that you are using and you think it is helpful. You can post it over here. So it's just a little place for you guys to kind of exchange tips about how to study for classes and so on and so forth. I have posted certain items over there, and it's completely optional. Okay, you can read it or you can just leave it alone. You can totally disagree and just say, oh, this is just bullshit, I'm not going to do that. That's perfectly okay as well. Okay, so it's just things that I am sharing with you, but I'm not trying to get anyone to actually use it. Alright, so that item is checked. There we go. So now we can get back into the class content. So to get back to the class content, last time we were talking about nope, not this one. This is for the new stuff today. So last one we were still talking about physical states, truth, numbers, and computer, and we got to 3.3. Basically we were done with 3.3. And I think we noticed that we have a NAND gate, right? It is a negated AND, and this is the truth table of negated AND. I believe that's where we left off. Is that correct? I mean, I can probably just watch my own video and just kind of fast forward to the end and find out whether that is the case or not. But I think that is the case. I think that's where we left off. Okay, no comments in the text channel. Oh, okay, Mark is typing. Yeah, so I think so too. All right, so what we'll do today is to look at the NAND gate. We'll talk a little bit about notations, and then we'll talk about how the NAND gate, okay, NAND, is actually, well, if you need to have only one kind of gate or one kind of operator, this is what you need, okay? Because that one little operator, and I'll talk a little bit about the correlation or the relationship between an operator, which is like ampersand in C++, versus an AND gate in a circuit, because they are very similar concepts, except one is an expression which is designed to be expressed in a text file, and then the other one is a symbol that you use in a circuit diagram. Okay, but they're really trying to express the same thing. What we see as the left-hand side and the right-hand side of an operator are the input pins to in a gate, and then the result of an operation is the output pin of a gate, and that's it, right? I mean, that's how the concepts map from programming to circuitry. All right, so let's go ahead and get to section 3.4, and in section 3.4. It talks about how NAND is the one gate that we need. Okay, we don't need anything else. So when we use NAND, if you look at NAND as an operator, for some reason the mathematicians like to use the up arrow symbol here. So if you want to find out how to type this in Markdown, you can right click on it and then click on Show Math As, and then go to Tech Command. TEX, what looks like TEX here is actually Tau Epsilon Chi in Greek. So it's basically just a backslash up arrow. Okay, that's how you enter the up arrow symbol inside a math equation thing. That actually works in Canvas as well. So in the HTML editor of Canvas, you can go into the equation editor and then you go to the advanced mode. Then you can just type LaTeX, like all of these things here. They're all specified in LaTeX. So learning LaTeX can be helpful, if you want to use that in your other classes too. But once again, this is some extra stuff that you do not have to do, but I just felt that, it might be helpful to some people. All right. So now we are going to look into negation, and negation has this symbol, the little horizontal thing, and then a drop. That is the mathematical symbol for Boolean or logical negation. So this is basically saying, not x is x NAND x. So the question is, does that make sense to you? So let me go to the text channel and see if there are. Oh, okay. I see. Okay, so in the character map, there's also an up arrow. Cool, cool. And there's also the negation symbol. Very good. All right, so the first thing we want to look at this is to say, well, that's what tech is claiming. But how do I know that is true? Okay, that this claim is valid, right? So that kind of goes back to study habits. Okay, because I don't want you guys to just kind of write down whatever I say and just go, okay, since the professor said, blah blah blah, okay, that has to be true. Nope, I want you to question the validity of everything that I claim, because that's an exercise. Okay, this is an exercise for you to basically start your journey into critical thinking. Okay, you got to ask, okay, is that right? How do I know whether that is right or not? Okay, you have to try to be able to answer those questions by yourself. Okay, so now let me kind of put this in a notation where we are all much more familiar with, and then we'll try to figure out, okay, how do we show this? So for that, I am going to switch to my little note-taking screen over here, and I'm going to make a little I'm going to make an expression first. Okay, so I'm going to make an expression that is just basically saying what I want to express. So we have the negation of an expression x. Okay, so x is not really a variable, it is really an entire expression, and I want to ask the question, is it really the same thing as the following? Is it really the same thing as the negation of x and x? All right, so when we look at this equality here, or basically it's a question of whether the equality holds or not. And this is specified in C, C++, syntax. So I'm hoping that all of you understand what this means. Okay, x is really just a Boolean value, and I'm asking the question of whether whether not x is really the same thing as not, and then x and itself. So it seems intuitive, right? So how do you prove this? I'm gonna ask you guys, how do you prove this? And I'm gonna go switch back to the text channel and see what kind of response I'm getting. A good job finding that character map for negation. All right. All right. So below is right. Okay, you can use the identity because x and x is really just x. So you can solve this using Boolean algebra. Okay, so that's basically the use of algebra. And Igor is correct as well, using Boolean algebra to solve this. Okay, very good. You can simplify. Okay, right. Okay, so, and I like Hong Hu's suggestion using a truth table. So we're gonna use this technique to prove that these two are exactly the same thing. So in order to do this, I'm making a table, and I can show you how to make a table in Markdown. Some of you probably know how to do that already, but I'm gonna show you guys too. So in this case, we have one independent variable. If x evaluates as true, then true and true. Yep, Okay, so very good. But I want to make this systematic, okay? Because this one, for this case, is really super duper easy, right? But later on, we're gonna have something that's more complex. So I want to find a method. I want to find a way of doing things that can also be applied when the expressions get more and more complicated, where you cannot just go like, I can just simplify this, right? But this one is it's simplifiable, but there's one that is not exactly simplifiable, so we're going to get to that one later. So I'm going to make a table here. This is a vertical bar, and then we have one independent variable. In fact, we have only one variable in this case, so it has to be the independent variable because it is the only variable here. And then we have the negation of x, and then we have x, or the negation of x and x here. There we go. So when you look at the Markdown side, the backtick is basically, it allows me to make an inline code block, and it doesn't really specify the language, so there's no syntax highlighting here. And to turn this into a table, I need to give it the bar dash bar dash bar in this case because we have 3 columns. And then from here on, we can type the actual value for each row. So x can be false, right? So when x is false, not x is going to be true. And since x is false, false and false is false, not false is true, right? So there goes one row, and then we only have one more row because with one single Boolean independent variable, we only have 2 cases. So the other case is when x is true. So when x is true, not x is going to be false. And since x is false, false and false is false, not false is true. Oops. Oh, excuse me. Forget that. When x is true, true and true is true, the negation of true is false. So now we have another false over here, and there we go. So we have just used a truth table to prove that not x is exactly the same as not x and x. Okay? So I know this one is trivial. Most of you can solve this using Boolean algebra, and you don't have to resort to the use of a truth table. But the technique of using a truth table is very, very useful in general. So that's why I'm introducing the technique, because later on we have some other expressions that are not nearly as easy to express or to simplify as this one. All right, next one up is conjunction. So here's conjunction, and conjunction in mathematical symbol is kind of like an inverted V symbol. So on this side it says x and y, and then on this side I'm not using any operator other than NAND. So on this side we have x NAND y, NAND x NAND y. So the first question is, does that make sense to you? That x and y is really the same thing as x NAND y, the whole thing, NAND itself. Or better yet, I am going to re-express it over here. The question is, oh, okay, let me switch to this particular tab. Then I can type, the equivalency that I'm trying to illustrate here. So the what I'm trying to show is whether x and x, is this really the same thing as the negation of x? Oops, sorry, x and y. There we go. Is this really the same thing as the negation of x and y? And then we have another NAND on the outside. There we go. All right. So the first question is everybody seeing how this equivalence expression is really the same thing as what you see in the notes here, which is this one over here in section 3.4.2. Let me kind of peel this one off so we can do it side by side. Give me a second here. There we go. And we'll put this one right here. Sort of, side by side. Now it's like close. Okay, there we go. Kind of close, but not exactly side by side. Another truth table. Yes. So we can use another truth table, and or you can also, just that is not right. Not NAND is AND. Yes, that's right, exactly. So Bernard is correct, because not NAND is AND. So this is NAND, and then when you NAND something with itself, it becomes not. So we are really just looking at a not x NAND y, which is the not of the negation of x and y. So now we have double negation, which cancels out, and we are just left with x and y. That is correct. That's okay. I mean, Bernard, sometimes we forget stuff if we don't use it, right? So, I'm not. CISP 440 is not a prerequisite of this class. So it's perfectly okay, if this is, reminding you of something that you learned in CISP 440, great. That means it is still in your mind. You just need to index into that memory. Once I mention, oh, okay, this is how it works. All right, so Igor is looking ahead, because with this one we don't need De Morgan's law. The next one does. Okay, so the next one is OR. So in this case, we're trying to express OR, but only using a hierarchy of NAND operators. So what you see here, that looks like a little V symbol, that is the mathematical symbol for OR. And the way I derive it is x or y is the same thing as the negation of x or y. So once again, I'm using double negation, but this time it looks kind of stupid, right? Because we started off with something that is very simple, very clean, and tech has to introduce double negation to make it look a little bit more complicated. But the reason why I introduce the double negation here is so that I can take the negation of an OR and turn that into not x and not y, because that is De Morgan's law. Now, this is not CISP 440, so I'm not going to spend too much time to talk about De Morgan's law. But it is a place where a mentioning of De Morgan's law can come in handy. So I'm going to do that. I will mention it, even though it is not super duper important in this class for you guys to understand De Morgan's law. So let me see, what do I want to do. I can put this back into this window. There we go. And then I'm going to explain what is De Morgan's law. Now, there are two De Morgan's laws. Okay, in other words, it comes as a pair. So we'll go ahead and specify De Morgan's law, or laws in this case. All right. So the first one, I'm just thinking, whether to use the C++ notation or whether to use the mathematical notation. I'm going to stick with the C++ notation here, just because, everybody knows that one. So, at this point of the class, I think that's probably a better way to do it. So we're going to look at the negation of x and y. And this turns out to be the same thing as the negation of x or the negation of y. So how do we know there is an equivalency here? This one is not obvious, right? This one really is not obvious. There's no other way to prove it. You cannot use Boolean algebra to prove this one. So with this one, you really need to use a truth table to do it. Okay, so I can help you set up the truth table, but I'm not going to fill up the cells in the truth table. And I'm going to leave it up to you guys to do it, okay? Because I think that's a good exercise, especially for those of you who have not been exposed to the concept of a truth table. So with this particular truth table, we have x and then we have y as two independent variables, which basically means the value of x does not depend on y, and then the value of y does not depend on x. each one is a Boolean variable, which means each one can be false or true. So that will give us 4 cases, altogether. And then what we also need to evaluate is the negation of x and y, like so. And then we also want to evaluate the other expression, which is the negation of x by itself, or the negation of y, like so. All right. And then we'll need to this is basically telling Markdown that I'm creating a table, and the row above is the header. So now we can fill in the content. X can be false, Y can be false at the same time, and I am gonna leave it up to you guys to figure out the values of the other 2 cells, because you just have to evaluate the 2 expressions. Evaluate this expression when x is false, y is false. Evaluate this expression when x is false, y is false. And then while x is still false, y can be true. So I want you to evaluate those 2 expressions. When x is true, y can be false, and evaluate the other 2 expressions, and then they can both be true. X and y can both be true, and go ahead and evaluate both of the expressions. And I'm going to leave it up to you to do this, okay? Because this is definitely something that you can do, and that will give you a chance to practice, what it is like to use a truth table to establish the equivalency between your 2 expressions. Alrighty. So with De Morgan's law, okay, so De Morgan's law, it will take us from here to here. Okay, that's the application of De Morgan's law. But once we take it from here to here, we recognize that this negation here is applied to the and over here, which basically means we have a NAND. So we have not x NAND not y. So now we need to turn negation into NAND, but we know how to do that already from here. So we end up with x NAND y NAND y. Alrighty. So do we have any questions about section 3.4? Are there any terms, any concepts in section 3.4 that you want me to go over? All right. What would these be used for? Well, I'm not sure exactly what these is referring to, but what section 3.4 is really, my cat is screaming in the background. It's carrying its little stuffed baby around, and just announcing that, oh, I'm a daddy, come look at me. Yeah, it's a little noisy in the background. Anyway, yep. Anyway, so the whole point of section 3.4 is forget the operators that they taught you in C and C++ when they say, oh, you need to know about negation, you need to know about conjunction, and you need to know about disjunction. They lied. All you really need to know is NAND. NAND is the only operator, the only Boolean operator that you need, because you can use it to make the other ones. Now, well, my avatar is 1 cat, but I have 2 cats. It's the other cat that's screaming right now. So maybe I will change my avatar someday so you can see the other cat. Anyway, so the whole point is, you can use NAND to do everything. So the bottom line, okay, what is the big deal of this, right? Okay, so, mathematically and theoretically speaking, we have this kind of really obscure operator that can be used to make up all of the other operators that we are used to. Well, the whole thing is we can now, if we can make a lot of little NAND gates, we can use an array of NAND gates and control the interconnection between the NAND gates in order to make all the circuitries that we need to do. And this is basically, this is your homework assignment, right? From Tuesday. So this one only uses what? 4 transistors. It has 2 p-type transistors and 2 n-type transistors. So that is kind of the smallest unit, the smallest gate that we can use, that we can make up using transistors. So as we will see later, okay, this class is taught in a very strange way because most people who teach C, C++, object-oriented programming, they really like the concept of top-down, right? This class is entirely opposite. It is bottom-up. We start off with transistors, and then we move up to the next biggest unit, or the next smallest unit, sorry, the next smallest unit, which is a NAND gate. And then from here, we move up to negation and OR, just using NAND gate. In other words, we are starting off with the smallest thing that you can use to make a computer, and then we're building up larger and larger constructs. And then at some point, we're going to end up with a processor. So that's going to be in about week 8, okay, that we'll end up with a processor. Why is this class taught after 360 instead of before? Well, that's actually kind of necessary because we need to first understand what is and or not, right? And those concepts were taught in CISP360. And then later on, we will learn how to translate constructs in C and C++ into assembly code. And that is why CISP360 is a prerequisite of this class. Because, I'm going to make the assumption that you know about what is a subroutine, what is a local variable, what is a parameter, how do you return a value, and so on and so forth. So all of those are going to be assumed. It's not important at this point, but it's going to be important when we get to the point where we can start to write code in assembly code. So I hope that answers the question. What was before the transistors? I'm not sure whether you're referring to my notes or whether you're referring to historically speaking what is before. So historically, what is before transistors are electromechanical devices, kind of like relays, right? If you look into, if you go to an auto shop, okay, you can, not auto shop, but places that sell parts for cars, you can find relays. So that's an electromechanical device, and those can also be used to make up computers. I mean, it's not going to be the best computer you can put together, but you can definitely use those to make computers too. My watch just buzzed, which means it's time to take roll. Yay! Alright, so let's go ahead and take roll. And this time I came prepared. Which is not usual for me. I don't usually come prepared. Alright, so this is the row taking activity for today. I'm just going to make it visible. And I'm going to type the word in the row taking, in the text channel right now. It is Heptapod. Heptapod. And I'm going to double check because I'm pretty sure it is, but it doesn't hurt to double check. Because occasionally I do make mistakes. Well, okay, let's just say more than occasionally. Okay, there we go. Heptapod, that is correct. Alright. So this is also a check of, how you are taking a class, okay? If you just look at Heptapod and go like, okay, let me just see how it's spelled, Heptapod. I'm just going to copy that into the activity, and I'm done. And I'm okay now. We can just proceed, okay? Or are you asking the question of, what exactly is a heptapod? What does it mean? And I'm going to Google it. What exactly does that word mean when we say heptapod? So that's a... Okay, it's... Well, heptapod as a word is not an alien. It means 8 limbs. I mean, sorry, 7 limbs. Hepta is 7. Octa is 8. So it's a being that has 7 limbs, and coincidentally, that is also the alien, or the kind of alien in what's the name of that movie? Arrival, that's right, exactly. So that's kind of where the word comes from. All right, cool. So we can now get out of this one and see what else we have to finish over here. Oh, okay, there we go. So section 4 is that is not hepta. As far as I can see, there are only 4, so that would make it a quadrupod, quadrupod, which we have a lot on Earth, right? Because we have a lot of four-legged animals. Insects are hexapods because they have 6 limbs, and then spiders are octopods because they have 8 limbs. Having 7 is unusual. Alrighty, so what we're going to do now is to look at the concept of a number versus the concept of a value. Because a lot of people look at these two things and they say, well, I don't see any difference. So what is the difference between a number versus the concept of a value? How are they different? And this is also why having a webcam is useful, because now I can show you a value right here. Okay, I have to kind of look at my own webcam. So this is a value. Okay, how many fingers are up? Okay, that's a value. Now if you say that's just 7, well, that's a number. Okay, because 7 is a digit. It can also be 111 in base 2, right? It can also be 11 in base 6. It can be 12 in base 5, and so on. That is the difference. In other words, value is really just the number of things that you want to count. But how you represent that quantity is a number. So number is kind of like a name, and the value is basically the person, the individual that the name is trying to identify. That is the difference between the two. So with that in mind, we are now ready to move on to hopefully get to a place where you can understand why I use the word heptapod. So we are moving on to the next module. The next module is values, numbers, and bases, right there. And I'm hoping some of you, or all of you, I'm actually hoping all of you have time to kind of preview this particular module, and because it's going to be helpful. Alright, so when we get here, the first thing I'm going to do is to explain what a number is, okay? Because you guys have been using numbers all your life, okay? But do you really know what a number is? And we're going to start with something that seems pretty, silly. Okay, we're going to start with 729. Okay, so we're going to look at 729, and I'm going to ask you, well, this is a number, right? We can see the 3 digits. We got 7 as a digit, 2 as a digit, and 9 as a digit. So the question is, what is it representing? And you guys gonna go like, well, everybody knows, everybody, even from the first grade, is going to know that this is 729. Yep, Omer is correct. Hepta is 7, pod means foot, and yep, so that's really good. Knowing the roots of words can be very helpful. Alright, so 729. So what exactly is it? It is 700 plus 20 plus 9. Right? I mean, there's no big deal to it. And I can see Igor is already knowing exactly where I'm heading. Very good. Okay, that's a very good thing to do. Because now I can say, I can repeat what Igor has already put into the text channel and say, this is actually 7 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 9 times 10 to the power of 0. Wow, great. Tak, you just took a really simple concept and then turn it into something that is unnecessarily complicated, right? Because we started off with 729, and now I'm re-expressing it as 7 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 9 times 10 to the power of 0. But this is what the number really is. Okay, this is actually what the number really is. Each digit in a number is telling you the quantity of a base to a particular power. So the 7 in 729 is telling me that there are 7, that's the quantity, of 10, which is the base, to the power of 2. And then the 2 is telling me that we have 2 of 10 to the power of 1, and then the 9 is telling me that I have 9 of 10 to the power of 0. So that really is how we look at a number. Okay, the interpretation of a number, given that it is using a specific base, is just this. Okay, each digit is telling us the quantity of a base, the chosen base, to the power that is correlating to the position of the digit that is in question. So let me just kind of pause here because I want to make sure that you guys are understanding all what I just said. How would this look like if you did it in base 16? Well, we'll get to that because we have to get to base 2 first, or it's easier to get to base 2 first. I can jump to base 16, but let's go ahead and use base 2 as a bridge. So do we have any questions about the concept that I just talked about? Okay, each digit in a number is the quantity of the base raised to the power that is correlating with the position of the digit itself. All right, I'm not seeing any questions. All right, so if this is okay, let me just ask you this question then, because now we're getting to the heptapod thing, right? So I'm going to ask you, what is 3 to 6, in base 7? So there are two ways to signify that we are using a specific base that is not 10. One way to do it is to use a subscript. So when you see 4, 3, 6, with a subscript, or subscript of 7, that means 436 is not 436, it is 436 in base 7. So the question is, what is it representing? What value is it representing here? So what we do is we're going to do exactly the same thing as before. We're going to break it up to 400 in base 7 plus 30 in base 7 plus, oops, oh, I just moved the plus in the wrong place here. There we go. And then plus 6 in base 7. All right, so everything is still in base 7 here. But we know what 400 in base 7 really means, because all that means is we have 4 times 7 raised to the power of 2. And then 30 in base 7 is 3 times 7 raised to the power of 1. And then we have 6 times 7 raised to the power of 0. So at this point, we can just kind of finish up the calculation. I don't have any space here. I'm going to move to the next row here. There we go. All right, so let me kind of get rid of the stuff that I don't need. There we go. So at this point, we can now say, oh, okay, so 7 squared is 49. So we have 4 times 49 plus, let's see, we have 3 times 7, right? So we have 3 times 7. And then we have 6 times 1. So we have plus 6 times 1. And now it's really just a matter of, adding up the numbers, right? So 4 times 49 is 196 plus, so we have 196 plus 21 plus 6, And let's see here. My mental math is not really that great, but I will try. 21 plus 6 is 27. So it's 223. There we go, Chris. Good job. You beat me to it. In base 10. So 223 is a base 10 number. Alright, so let me go back to the text channel. So the number, when you expand it into powers of 7, still works like each digit is a power in the 100th place in terms of power of the 7. So the key is the number of zeros after the digit is dictating what power of the base we are referring to. So with 2 zeros, we are raising 7 or whatever the base is to the power of 2. If you have 1 0, we're raising it to the power of 1, and so on. But that really kind of begs the question of, what if we have decimal points? What is a decimal point doing, right? Alright, so let's try to figure out the mystery of the decimal point. So let's just look at the 3.14, okay, as a base 10 number. So if I don't specify a base with a subscript, it is by default base 10. So what exactly is this? Okay, fine, Tech, you're going to do something really unnecessarily complicated again. Okay, exactly. So Igor is right, because we are now moving to the negative base. So now we still have a 3 times 10 to the power of 0. Yeah, it's still here. But this time the 1 is referring to 10 raised to the power of negative 1. And then the 4 is referring to the quantity of 10 to the power of negative 2. So it still works, right? I mean, it's just that, the power that we are raising, the base to, is no longer non-negative. Now it's moving into the negative portion. And then Ian is typing, so it's broken down into the non-placeholder integer multiplied by its base squared. Not quite sure what that is referring to, what it is referring to. But the idea is we just keep going, okay? It's a convention that the most significant digits are on the left-hand side, and then the least significant digits are on the right-hand side. But we basically just start with the most significant digit and say the next one to the right-hand side has one power less than the one to the left-hand side, and we just keep going. Shouldn't it be plus 0.04? But that is 0.04. 4 times 10 to the power of negative 2 is 0.04. Oh, right. Okay, I see. Yes, so I got that one. I got that part wrong. Sorry about that. There we go. Thank you. So yes, Emily is correct. Okay, I stand corrected. It is 0.04, not 0.4 over here. Thank you. Cool. All right. So what is the purpose of the decimal point? Okay. Without the decimal point, we would not know where is the digit corresponding to the quantities of whatever base raised to the power of 0. So the point is just a marker. It's a little bookmark that is telling us, see these, this whole bunch of digits over here? Let me tell you which one is corresponding to the base raised to the power of 0. It is the one digit that is immediately to the left-hand side of the decimal point. That's what the decimal point really is for. It's really just a little bookmark that tells us, hey, let me tell you where the unit is. Okay, where is the digit corresponding to the base raised to the power of 0? Because whatever is to its left-hand side, we have the positive powers, and then whatever is on to the right-hand side have the negative powers. But it works out the same way. So that's one way to look at different bases. So how do we write 0.2 in binary? Well, we're going to get to that. It's not easy to write point 2 in binary. Unfortunately, something that seems really easy is not really that easy. Okay, so we'll get to that. So next thing is, how do we do base conversion? Because right now, we are basically looking at how a value is represented by a number. In other words, how do we interpret a number that is not in base 10, which we're used to. So now we want to kind of flip it around and say, okay, so what about given a value, kind of like what Tam just kind of presented. What if we are given a value and we want to represent that value in a specific base? So that is the next question. Okay, well, it doesn't matter. Decimal point, decimals in any base, works exactly the same way. It's just that we are not used to it because we have been poisoned by base 10 ever since what, elementary school or even before. Yes, I did use the word poison because base 10 is an awful base to use just because we got 10 fingers. We might as well use base 7. I mean, it really is not that good of a base to use. All right, exactly. So we are decapods. No, we are, well, okay. We are decadigit, okay, because we got 10 fingers, but we only got 4 limbs. All right, so let's move on and talk about base conversion, okay? This time we are given a value and we want to convert it into a specific representation. And I'm just looking at the time. We got plenty of time. But instead of doing that first, I'm going to ask you guys to think about how we can use coins and bills in order to make up for a particular amount of money. Okay, so I'm switching the problem around a little bit, and let's just say that we have this amount as a change, at McDonald's to a customer. So we are hypothetically working at McDonald's now. So we have the dollar amount is, I'm gonna have to pick something that is at least a little bit interesting. So let's pick $18, and I have to pick something that is doable, so it's not and 75 cents. Okay, $18.75, and let's just say that we use all the usual denominations, so we don't use the unusual denominations. So how do we make a change of $18.75? You guys are going like, oh man, this is so easy, right? I mean, we are in college, taking a programming class, and you're asking us, how to make a change. Well, I'm going to be the first one to answer the question. We can do this with 1,875 pennies. That will work, right? So just imagine the scenario, okay, of me working at McDonald's, and I'm asking, soup, we don't have enough pennies. Why do you need pennies, Tack? We got plenty of pennies in that register. Because I need to make change for $18.75, and I don't think we got 1,875 pennies in the register. I think we need more pennies. That's not gonna work, right? I mean, I guess I'm not gonna go back to work over there the next day. So how do you make change? So you guys look at this and go like, okay, Tack, let me show you how to do this, right? So with $18.75, we look for the largest denomination that is less than or equal to the amount. So 20 is greater than. Let's not consider 20. So we'll try 10. So we're gonna say we got one $10 bill. Okay, cool. So with one $10 bill, we have $8 left, right? $8.75. And then we look at, oh, okay, a $5 bill is going to be the next one. We need one of the $5 bills. So that's going to take care of, I'm going to use the bulleted list thing. There we go. So the next one up is going to be what? We have $3.75 left. So, yeah, a $2 bill. Well, that's why I said we're going to use the common denominations, because $2 bills are not common. So we have the next one down is a $1 bill. So we're gonna say 3 of the $1 bills. And then we get to the 75 cents, right? So we have 2 quarters. Yes, I know there's a half dollar. Not half pennies, half dollars. No, we do not have half pennies. As far as I know, we don't have half pennies. And it is illegal to cut a penny in half. Okay, so the next one down is we got quarters. So we're gonna have 3 quarters to make up for the 75 cents, and we are done. The British pre-decimal half penny coin. That is interesting. But from the mentioning of Elizabeth, I'm guessing this is not a United States currency denomination. Well, yeah, slicing a penny that way is still destroying the currency, which is illegal. All right, so what is the whole point of doing this? Okay, you're wasting my time, Tech. Well, the fact that you can do this without even thinking much about it means you know base conversion already. Because making change for $18.75 is actually a lot harder than base conversion. It's just the way we look at things. It's a perspective kind of thing. So let me explain first why I said this is actually difficult. Because the first or the least of the denomination is a penny. So okay, it's not doing the spacing right on the left hand side. That's okay, it's not a problem. So we got a penny, right? And then the next one up, okay, multipliers of denominations. Okay, there we go. Okay, now everything looks right again. So we got a penny, and then the next one up is a nickel. Next one up is a dime. Next one up is a quarter, and we're gonna skip the half dollar, so we get to the $1 bill, and then we're gonna skip the $2 bill. We go to 5, and then we go to 10, and I'm gonna do like 2 more steps, and then we'll stop. Okay. All right. So these are the denominations commonly used in the United States. And if you look at the multiplier to go from one to the next denomination, let's see if there's a pattern to it. Okay, so right here we have a 5x, to go from a penny to a nickel, and then to go from a nickel to a dime is a 2x, and then from a dime to a quarter is a, guess what, 2.5x. It's not even a whole number. And then from that to a dollar is a 4x, and then we're going to get back to 5x again. So you might say, oh, okay, maybe we're just repeating the pattern again. Sort of. Because we have another 2x again, and you would think that we have another 2.5x because it's a cyclic kind of thing. No, we have another 2x first, then we have the 2.5x. There is no regularity. Even though we have, even the 2x appears multiple times, and 2.5x appears twice, and 5x appears twice too, and then 4x appears exactly just once, but there's no pattern to it. This is like crazy, man. I mean, this is like, who thought of this stuff here? But we get used to it, right? But we can get used to this. But this is base conversion. This is really the essence of base conversion. And you guys go like, but I don't really see this as base conversion. So tax proposed currency denominations. All right, politician. Okay, my platform. The first reform that I'm gonna do is to change the denomination to something that makes sense. Okay, because this does not make sense to me. I'm gonna have to propose something that does make sense. So I'm gonna start with a $1/8, move on to a quarter of a dollar, and then move on to a $half, and then move on to a $1, then move on to a $2, a $4, $16, oops, sorry, 8, and then we get a 16, and then we get a 32. I mean, you guys can guess what the next ones are. So we got 64, 128, and so on. So I'm going to propose that we change our currency denominations as follows. Okay? You guys go like, so what does that have anything to do with this class? Okay, Tag, you have some political ambition, and this is your platform, and this is what the kind of reform you want to do. What does that have anything to do with base conversion? Well, just hold on to here. Okay, so we're going to get back to the amount that we want to change, which is $18.75. Okay, all right, so now let's do the conversion again. Okay, how do we make $18.75 but using the new currency denomination system? Okay, so we have so we're going to use the same approach, right? So we're going to look at the denominations, and we're going to pick the first one we're going to pick is the one that is less than or equal to the amount, which is the 16. So we have one of the 16, and after the 16 we have 2.75. So we're going to move down the currency, the denomination. We don't have an 8. So I'm going to specify that we do not have an 8. Okay. And then I'm going to specify we do not have a 4. And then when we get to 2, yep, we need one of those. And then we have none of the 1. And then we have 75 cents left, right? So with the 75 cents left, we have a $half. And once we have a $half, we need a $1/4, and then we do not need a 1/8 of a dollar. There we go. And you guys look at this and go like, okay, so what, right? I mean, what is the big deal here? You are looking at a binary number. You just have to tilt your head. Let me see. Clockwise, 90 degrees. Then you're looking at a base 2 number, and the base 2 number has a decimal point. So the question is, where am I going to put the decimal point? So I'm going to let you guys kind of chime in here. Between which two lines should I put the decimal point, or binary point in this case? You can see the line numbers, right? From line 77 to line 85. So if I need to put a decimal point, or the function of a decimal point, because we really should call this a binary point, where should I put that point? What is the purpose of the point again? Remember what I said a little bit earlier? It is just there so that we can put a separator between 82 and 83. That is correct. So the point would be between these two, because the whole purpose of the point is a separator. It separates the non-negative powers from the negative powers. And 1, 2, 4, 8, 16, those are the non-negative powers of 2. Half, quarter, and eighth, those are the negative powers of 2. So that means, okay, 18.75, what we see this when we see this as a base 10 number, if I want to re-express this as a binary number, it becomes 10010.110, and that's in base 2. There you go. That is base conversion. So the next time you want to kind of think about base conversion, or you want to explain base conversion to someone else, you can have that person to do a conversion, of just an amount of money first, okay? Because that's actually harder compared to base conversion, because base conversion is, at least, is consistent. Look at the look at all the values of the denominations. There's a pattern to it, and that's why I said, if you know how to make change, working for McDonald's, you already know base conversion. You just did not know that you know. Yes, I just said that. You did not know that you knew. Isn't that cool? Well, I think it's cool. All right, so let's do some really kind of oddball kind of base conversion. All right, let's do some really oddball kind of base conversion. We'll start at 1000 in base 10, okay? But we want to do this in base 7. So this is the time when most people would say, but why in base 7? This is insane. Who would use base 7? I will tell you who would use a base 7. Not the aliens. The aliens are smart, okay? I don't even think that they use numbers. I mean, they are so ahead of us, It would be octopus, okay? Octopus, like, those little soft-bodied animal underwater. And then you guys would say, but octo means 8, tag. Octo means 8, okay? And then hepta means 7. Well, think about this, okay? The octopus needs one tentacle to hold the beer when it's counting. So there's only 7 limbs left for counting purposes, and that's why they have to use base 7. See, these guys are much more, how should I put it? They're much more chill than we are. They always think, well, but I need one tentacle to hold the beer while I'm doing accounting and other things. So that's why they use base 7. It's very important. But there's actually a reason why I chose to use base 7 as an example. Yeah, and then another question is, how can octopus drink beer underwater? That is also insane. My answer is SpongeBob, right? There's no further explanation needed. You just have to watch SpongeBob, then you understand how creatures can drink underwater. Pretty easy. Yep. All right, so let's do this in base 7. Let's do the conversion, okay? So we'll start with 1000, and now we have to think about, okay, so what are the powers of 7 that we are talking about here? So it really helps when you say, well, 7 to the power of 0 is 1. And okay, I gotta do it in a bulleted point. So we have 1, we have 7, and then the next one up is 49. And then the next one up is 49 times 7, which is 300 and times 7. So 343, I think. Yeah, that looks about right. Alright, and I'm pretty sure that's enough because 343 times 7 is going to exceed 1000, so we don't need any more than that. Alright, so now the question is, we're going to start with the 343. How many 343s can we put in 1000? The answer is, looks like about 3 or less, right? I think we only got 2 of those. So it's 2 times 343. Okay, so this is not going to render correctly because the asterisk is also used to start italicizing. So I have to put it into a code block, a linear code block, in order to have this rendered correctly. All right, so what is left after 2 times 343? So that's what, 868. So we got 2, 1, and a 3. It's a 314. Oh, 314. Yep, okay. So it has 314 left. And how many 49s can we fit into 314? Well, we know it's not going to be 7. And 6 would do, right? So we have 6 of those. So 6 times 49 is 294. Okay, so 294, 314 minus that amount is what? 314 minus 294. So I'm looking at this. I really should have used a spreadsheet. 20. Good job. Good job. Okay, so 20 has 2 of 7s, right? So 2 times 7. That takes 14 of the 20. So we only got 6 left. Okay, so There we go. So 6 times 1. So, yep, good job. Okay, so very good. So now we can now say, okay, so based on this, the base 7 representation of what we know as 1000 is going to be 2, 6, 2, 6 in base 7. Yep, and that's coincidental. I just randomly chose a number to convert to base 7, and it turned out to be 2626. Kind of cool. Alright, so I'm going to pause a little bit here and see if you guys have any questions about the process. I can kind of explain the process in using the longhand. So the longhand to explain this, okay, I'm going to use equation in this case. So we're going to have 1000 is, let's see, 2 times 7 to the power of 3 plus the remaining amount, which is 314. Is that okay? So we kind of have to figure out first, how many 3 to the power of 3 do we have, 7 to the power of 3 do we have, and turns out we only got 2 of those. So the next thing we need to do is to figure out in 314, we have 6 times 7 to the power of 2, and then plus the remainder, which is 20 in this case. And then 20 in return is 2 times 7 to the power of 1 plus 6. And then finally, when we get to 6, is just 6 times 7 to the power of 0. So that's kind of the more step-by-step sequence of figuring out the base 7 representation of the quantity that we know of as 1000. Alright, so I'm gonna kind of pause. We are not done with the lecture yet. We still got another 6 minutes or so. But I do want to kind of pause to make sure that you guys understand the process. If you think about the money example, instead of having a multiplier of 2 when we're working with the denominations, it's going to be a multiplier of 7. But the idea is the same. Yep, that's base conversion. And I think I remember somebody asked about converting to base 16, and I cannot remember the value that person wanted me to convert into base 16. So let me see. I think it's 729 and want me to convert to base 16. So let's do that. Why not, right? 729 in base 16. Now, how do we do that? Well, kind of the same thing. Okay, so what I find helpful is to write out all the powers of 16 first. So 16 to the power of 0 is just 1. 16 to the power of 1 is 16 itself. And then 16 to the power of 2 is 256, which is enough in this case because 16 times 256, or 16 to 16 cubed, is going to exceed 729. So we probably don't need that power of 16 to begin with. All right. So now what do? We have to first find out how many 200. Okay, let me use the power here. 16 to the power of 2 fit into 729. So that question is quite easy to answer because you can use division, right? So you just have to divide 729 by 256. So the answer is 2. Okay, 2 of them. So now we have to look at the remaining portion. So the remaining portion is 729 minus 200 and no 512, and that turns out to be 217, I think. Yeah, that looks right. Okay. So now the next question is, how many 16 to the power of 1 fit into 217? Oh, okay. Well, that was quick. But I'm not using a calculator. Alright, so you do a division here. Okay, 217 divided by 16 is, we got a 116, and then we have 57 as a remainder. And we can have what? 3 fit into that. So we got 3 of them. Okay, so we have 3 of them. And then the remaining portion is going to be 217 minus 3 times 16. Whoops, nope, no. Not 3, 13 of them. Okay, I forgot 1. Alright, so there's a 17, oops, 13 of 16s times 16. And that turns out to be 208. So 208 is the product, so we have 9 left. There we go. Yep, so 2D9 is correct, but I'm doing this really step by step. So the last question, even though it's a trivial question, but I'm going to put it into this form because this is how we figure out a common step in to do something, because that's how programs are written, right? So we want to make things very uniform. The same method is reapplied with something being changed. In this case, it's really just the power of 16 that is being changed. So then the answer is 9 of them. So now we know the digits already, right? So we got 2 of the 16 squared, we got 13 of the 16 to the power of 1, and then we got 9 of the 16 to the power of 0. So when we write it out as a number, we can now say 729 is, okay, we start with a 2. Okay, very good, easy peasy, right? Then the next digit is a little bit harder because we don't have a single digit to represent the quantity of 13. Because we are so used to base 10, right? So in base 10 we have single digits to represent from 0 only up to 9. Okay, we don't have a single digit to represent 13. So that's why in hexadecimal number or base 16 numbers, we borrow the digits from the alphabet. So in the alphabet we have A to represent the quantity of 10, and then we have B to represent the quantity of 11, C to represent the quantity of 12, and then D is the one to represent the quantity of 13. So that's where the D is coming from. And then the 9 is pretty easy because we only got 9 of the 1s, or 16 to the power of 0s. So that's why it is 2D9. So Patrick is right. Okay, Patrick's answer in the text channel was right. So how did you figure that out, Patrick, so quickly? I have to ask, yes. Okay, very good. Yep. That's a lot of mental math to do quickly. Yeah, I have to say that is the case. And then Bilal said, so A is 11. No, A is 10. That's what I said. A is 10 because 9 is the highest single digit that we have in base 10. So 10 itself, the value of 10, is represented by a digit called A in base 16. Yep, there we go. All right, so we are almost out of time. We are indeed out of time. So I'm going to get you guys started with the lab. But before we go there, let me ask you guys, what do you think is the largest base that is in use commonly in computer science? So I'm going to let you guys think about that when I open up the lab for tonight. So once again, the question is, what is the highest base? Okay, so base 10 is higher than base 2, base 16 is higher than base 10, and so on. So what is the highest practical base that we actually use in computer science? Or in computer industry? It's not really computer science per se. It is in the computer industry. And we got a few people typing. Very good. That's participation. I like participation. Not quite 128. Well, not as far as I know, but 64. Yes, 64 is the answer. So base 64 is how we encode binary data into an ASCII stream, like HTTP. Yep, 64 is the answer. Alright, so the next lab is NAND 2. So just like the previous lab, it has a very, very short quiz, okay, worth only 3 points. And then it also has a file submission that is worth 4 points. But this time, everything is due tonight at 9:50 p.m. Why? Because, well, guess what? I'm assuming that you guys are remembering how to use Logisim from Tuesday. Yes, that's an assumption that I'm making. And I'm also assuming that you're remembering the concept, like what is a splitter, what's an input pin, what's an output pin, and so on and so forth. So what you need to do tonight is significantly less compared to what you need to do on Tuesday, and that's why I'm not giving you too much extra time. No extra time for the file submission. All right. So getting back to the text channel, okay, you guys need to know the key to NAND 2, so I'm gonna give you the key first before I address the questions in the text channel. Let's see. Yep, Nandroid. Yep. So Nandroid is the access key to the lab. Alright, so let me answer the questions. Well, 64-bit operating system has nothing to do with base 64. Okay, alrighty, cool. Alright, so you guys can get started with your lab. I will probably go away, for 5 minutes or so, get something to drink, and then I'll be back to answer questions. Alright, so I'm just going to re-emphasize one more time that both the lab and the file submission are due tonight at 9:50 p.m. because I know certain people have a tendency to do everything at the very last moment. So I just want to re-emphasize that everything is due tonight. Okay, do not make the assumption that this is due next week sometime. Alrighty, so I'm gonna stop the live stream now. But I will stay online, after I come back in about 5 minutes, and then we'll do the lab. And if I don't see you again, have a nice long weekend. And I will probably use the announcements to send you guys, some recommended activities to do over the weekend. Yes, I know it is the weekend, but since we have 5 days before we meet again on next Tuesday, I think it is important to kind of do something with this class just so that you can keep the concepts in your mind so that next Tuesday when we meet again, it's not going to be like, oh, but I forgot everything that we talked about last week, which happens quite often with this class because we move really fast in this class. It's a very packed class in terms of content density. So that's why it's really important to kind of keep all the concepts in our mind and not to lose track of that stuff. Alrighty, so I'm gonna stop my live stream, and I'll be back to answer questions in 5 minutes.